What if the clock on your wall isn't measuring time? It's just measuring change. Think about the last time you watched a rocket launch from Kennedy Space Center. That thunderous countdown. 10, 9, 8. We treat every single second like it's a rock-solid, unchangeable fact of the universe. But what if the greatest minds in physics are now telling us that time, as we know it, might be the biggest illusion ever pulled on the human mind? Welcome to Astromat, where we take the wildest corners of space and physics and make them make sense. I'm so glad you're here today because this one is going to genuinely mess with the way you see reality. We're breaking down 10 of the most compelling theories that suggest time is not actually real. And trust me, you're going to want to stick around until the very end because the last few theories build on each other in a way that'll completely reframe everything that came before. If you love science that actually blows your mind and still makes you go, oh wow, I get it, hit that subscribe button right now and join the Astromat community. Let's get into it. Let's start with something you do every single day without even thinking about it. You check the time. Maybe it's your phone. Maybe it's the clock on the microwave. Maybe it's that watch your dad handed down to you. And in that moment, time feels as real and solid as the floor beneath your feet. But here's the thing. That clock isn't measuring time. It's measuring change. Think about it. Every clock ever built, from the sundials of ancient civilizations to the atomic clocks NASA uses to synchronize deep space missions, every single one of them works by tracking something that moves or oscillates or shifts. A pendulum swings, a crystal vibrates, cesium atoms pulse at exactly 9,192,631,170 cycles per second. We count those changes, and we call that counting time. But what if time itself is just the name we gave to the fact that things change? This was actually one of the earliest cracks in the foundation. Philosophers and physicists noticed something quietly unsettling. You cannot point to time. You cannot bottle it, weigh it, or detect it directly. Every instrument we have ever built to measure time is really just measuring motion, repetition, and change in the physical world. Here's a thought experiment. Imagine the entire universe suddenly froze. Every atom stopped moving. Every photon of light halted in place. Every particle locked still. Would time still be passing? Most people instinctively say yes. But physics says maybe not, because if nothing changes, there is no before and no after. There is no sequence. And without sequence, what exactly is time doing? This idea connects to some of the deepest questions in cosmology and space science. When NASA scientists model the early universe, fractions of a second after the Big Bang, they are not just describing what happened in time. They are describing how the conditions for change itself came into existence. Time, it turns out, may not be the stage on which the universe performs. It might just be the performance itself. And once you see it that way, you are ready for something even more unsettling. What Einstein discovered about time when things start moving really, really fast. Now here is where things get genuinely strange, and I mean that in the best possible way. In the early 1900s, a young patent clerk in Switzerland started asking a question that most people never even thought to ask. What if the speed of light is the same for everyone, no matter how fast they are moving? It sounds simple, but the implications of that one idea cracked the concept of time wide open. Albert Einstein's special theory of relativity revealed something that still sounds like science fiction even today. Time does not pass at the same rate for everyone. The faster you move through space, the slower you move through time. Not as a feeling, not as a metaphor, as a measurable, real, physical fact. Here's an analogy that might make this click. Imagine you and your best friend both leave Chicago at the same moment. You take the highway at 60 miles per hour. Your friend jumps on a supersonic jet. You both started together, but you arrive at very different times. Einstein showed that something eerily similar happens with time itself. Two travelers moving at different speeds through space will age differently, genuinely, physically differently. And NASA has proven this is not just theory. The GPS satellites orbiting Earth right now are moving fast enough and sitting in a different gravitational field strong enough that their onboard clocks run slightly faster than clocks on the ground. We are talking about microseconds per day, but those microseconds matter enormously. If NASA and the engineers behind the GPS system did not correct for Einstein's relativity every single day, your phone's navigation would drift by miles within hours. Relativity is not an abstract idea. It is baked into the technology millions of Americans use to get to work every morning. But special relativity was just the beginning. When Einstein developed his general theory of relativity, he showed that gravity does the same thing. The stronger the gravitational pull around you, the slower time moves. Near a black hole, one of the most extreme space science facts in the known universe, time slows so dramatically it nearly stops altogether from an outside observer's perspective. So time is not a fixed river flowing at the same pace everywhere. It bends, it stretches, it is personal. And if time can stretch and slow depending on where you are and how fast you move, then the next question has to be this. What if every moment in time, past, present, and future, already exists all at once? Okay? Take a breath. Because what we are about to explore is one of the most mind-bending ideas in all of modern physics. And once it lands, you will never look at a photograph, a memory, or a sunrise quite the same way again. Most of us picture time like a river. It flows in one direction. The past is gone. The future has not happened yet. And right now, this present moment is the only thing that actually exists. That is just how reality works, right? Not according to a growing number of physicists. There is a model of the universe called the block universe, and it comes directly out of Einstein's relativity. The idea is breathtaking in its simplicity and terrifying in its implications. In the block universe, space-time is not a flowing river. It is a solid, four-dimensional structure, like a loaf of bread. Every slice of that loaf, every moment from the Big Bang to the farthest reaches of the future, all of it exists simultaneously, already baked in, already there. Your birth. This moment right now, watching this video, every NASA moon landing, every future space discovery we have not made yet. According to this model, they are all equally real, equally present, just located at different coordinates in space-time. Here is an analogy to make this tangible. Think about a movie on a hard drive. Every scene, every frame, every moment of that film already exists on that drive all at once. When you press play, you experience it as a sequence. But the ending was always there. It did not come into existence when you watched it. The block universe says reality works exactly like that. We experience moments one at a time because of how our consciousness moves through space-time. But the full movie has always existed. This is not fringe science either. Physicists at MIT, Caltech, and Princeton have published serious work exploring eternalism and its relationship to quantum mechanics and cosmology. When NASA scientists calculate the trajectories of spacecraft years into the future with extraordinary precision, they are in a very real sense treating future moments as fixed, knowable coordinates, almost as if they already exist. The universe, it seems, may not be something that is happening. It may be something that simply is. And if that is true, if every moment already exists in a frozen four-dimensional block, then the next question has to shake you to your core. Why do the fundamental equations of physics work perfectly even when you remove time from them entirely? We have talked about how time bends and stretches. We have explored the idea that every moment might already exist inside a frozen four-dimensional block. But now we are going somewhere even deeper. We are going to the most fundamental level of reality that science has ever reached, the quantum world. And what physicists found there when they went looking for time is one of the most stunning science facts in the entire history of human knowledge. They found nothing. Let me explain what that means, because it is not nothing in a disappointing way. It is nothing in a universe-shattering way. In the 1960s, two brilliant American physicists, John Wheeler at Princeton and Wheeler-DeWitt, attempted something extraordinary. They tried to write a single equation that described the entire universe using quantum mechanics. They wanted one master equation that unified gravity and quantum physics into one complete picture of reality. The equation they produced is called the Wheeler-DeWitt equation. And when they wrote it out, something deeply strange stared back at them from the math. Time had vanished. The equation that described the full quantum state of the universe worked perfectly. It was internally consistent. It was mathematically coherent, and it contained absolutely no time variable whatsoever. Not a slowed down version of time. Not a stretched version of time. No time at all. Think about what that means. Imagine you are an engineer at NASA's Jet Propulsion Laboratory in Pasadena, California. You write out the complete equations governing a spacecraft's journey across the solar system, but when you finish, you realize the equations never once mention speed or motion or sequence. They just describe a state, a complete, timeless state. And yet the math works perfectly. That is essentially what Wheeler and DeWitt discovered about the universe itself. Now here is the thought experiment that makes this click. Picture two clocks in a room. Each one measures time relative to the other. From inside the universe, time appears to flow because we are comparing one part of the universe to another, one changing system to another changing system. But zoom out to a view of the entire universe as one single quantum system, and there is nothing left to compare it to. No external reference, no outside clock. And without an outside clock, the equation has no need for time at all. This idea connects directly to ongoing research in quantum gravity, an area where institutions like Caltech, MIT, and the Perimeter Institute are pushing the boundaries of space science right now, trying to reconcile Einstein's relativity with quantum mechanics into one unified universe-explained framework. The universe at its deepest level may be a timeless quantum state, and what we experience as time may simply be what it feels like to be a small, changing piece of something that is, as a whole, perfectly still. And yet, if time is truly an illusion, if the universe has no clock at its core, then why does every single one of us feel it moving in one direction, always forward, never back? We have arrived at the deepest question of this entire journey, and I want you to feel the full weight of it before we unpack it. If time is not a fundamental feature of the universe, if the equations of quantum mechanics work perfectly without it, if every moment already exists simultaneously in a four-dimensional block, then why, with every single breath you take, does time feel like it is moving? Why do you remember breakfast this morning but not tomorrow's lunch? Why does the universe seem to have a direction, an arrow, always pointing from past to future and never the other way around? This is what physicists call the arrow of time. And the answer connects the smallest particles in existence to the largest structures in the observable universe. It starts with a concept called entropy. Entropy is essentially a measure of disorder. And there is a law in physics, one of the most reliable laws we have ever discovered, that says in any closed system entropy always increases. Things fall apart. Ice melts, coffee cools, stars burn out, order dissolves into chaos. And crucially, this process only ever runs in one direction. Here is an analogy every American can feel instantly. Imagine you are watching a video of a perfect glass of iced sweet tea sitting on a summer porch in Georgia. The ice is melting, slowly, gracefully, into the tea. Now imagine that video running in reverse. The liquid suddenly assembles itself back into perfect ice cubes. You would know immediately something was wrong. Your brain flags it as unnatural. That instinct is you detecting the arrow of time. You are sensing entropy. Now here is where this connects to the universe explained at the grandest scale. NASA's observations of the cosmic microwave background, the faint afterglow of the Big Bang itself, show us that the early universe was in an extraordinarily low entropy state, almost perfectly smooth, almost perfectly ordered. And ever since that moment, the universe has been moving relentlessly toward greater disorder, greater complexity, greater chaos. That one-way march of entropy is what creates our experience of time flowing forward. We remember the past because the past was more ordered. We cannot remember the future because the future is where disorder increases, where information spreads out and becomes harder to reconstruct. Our memories, our sense of before and after, our entire lived experience of time, is essentially the universe's accounting system for entropy. Physicists at institutions like the Santa Fe Institute and researchers building on the work of Ludwig Boltzmann and more recently Sean Carroll at Caltech have spent careers mapping exactly how this thermodynamic arrow gives rise to the psychological arrow, the one you feel right now, reading this moment as present and last Tuesday as past. And here is the most breathtaking part of all. The arrow of time is not written into the fundamental laws of physics. Most of the core equations of physics, classical mechanics, quantum mechanics, even Einstein's relativity, work just as well running forward as they do running backward. Time's direction is not commanded by the deep rules of the universe. It emerges from the universe's initial conditions, from the extraordinary low-entropy miracle of the Big Bang itself. In other words, time does not flow because the universe demands it. Time flows because the universe started in an incredibly special, incredibly ordered state and has been unwinding ever since. So the clock on your wall, the memories in your mind, the feeling that right now is real and yesterday is gone, all of it traces back to a single moment nearly 14 billion years ago when everything began in a state of breathtaking order. And that means the next question, the one that takes everything we have covered today and pushes it one final step further, is this. If time emerges from initial conditions rather than fundamental law, could there ever be a universe where time runs in reverse or does not exist at all? So, let's bring it all home. We started today by questioning something most of us have never once thought to question, the clock on the wall. And what we found, layer by layer, theory by theory, is that time as we experience it may be one of the most beautiful and elaborate illusions in the entire universe. 3 ideas I want you to carry with you after today. First, time is not a fixed universal constant. Einstein proved, and NASA confirms every single day through the GPS satellites guiding your morning commute, that time bends, stretches, and moves at different rates depending on gravity and speed. It is personal, it is physical, and it is far more flexible than we ever imagined. Second, at the deepest quantum level of reality, the universe's own master equation has no time variable in it at all. The cosmos, described as a complete whole, appears to be fundamentally timeless. What we experience as the flow of time may simply be what it feels like to be one small, changing piece of something that is, at its core, perfectly still. Third, the reason time feels like it moves forward, the reason you remember yesterday and not tomorrow, traces all the way back to the extraordinary ordered state of the Big Bang. Time's arrow is not a law. It is an inheritance, a gift, or perhaps a consequence of how improbably structured the beginning of everything truly was. And here is why this is not just a universe mystery to marvel at from a distance. NASA's future missions, from deep space exploration beyond our solar system to the search for quantum gravity signatures in the cosmic microwave background, are pushing directly into these questions right now. American scientists and engineers are actively working to understand whether time is fundamental or emergent. The answers they find will reshape physics, technology, and our understanding of reality itself. Now here is the final thought I want to leave you with, and I want you to really sit with this one. Every moment you have ever lived, every laugh, every loss, every ordinary Tuesday morning pouring coffee in your kitchen, if the block universe is correct, if the Wheeler-DeWitt equation is telling us something true, then none of those moments ever disappeared. They do not exist in the past the way we think of the past as gone. They exist as fixed, permanent coordinates in a 4-dimensional structure that simply is. The universe does not delete its moments. It keeps them, all of them, forever. Science explained that to us. Not poetry, not philosophy, physics. If today's video gave you that feeling, that particular mix of wonder and vertigo that only the best space science can deliver, then you are exactly where you belong. Welcome to Space Secrets. Hit that subscribe button right now so you never miss a new video. Every single week on this channel, we take the deepest, most mind-expanding questions in space exploration, cosmology, and physics, and we break them down with clarity, wonder, and genuine respect for how curious and intelligent you are. New videos drop every week on Astromat, and trust me, what is coming next is going to be worth the wait. Stay curious. Keep looking up. Hey, thank you so much for watching this one all the way through. That genuinely means a lot. I hope the idea that time's arrow is not a law of the universe, but an inheritance from the Big Bang itself really stuck with you, because that one still gets me every time I think about it. And as NASA pushes deeper into space exploration, probing the earliest moments of the cosmos, questions like this stop being philosophical and start becoming the actual frontier of American science. I love exploring this stuff with you. Honestly, there is nothing better than sitting with a question this big together. I'll see you in the next one.